Right, so often I give talks where I really know where I'm going with it. This is not one of those times. So what this is I've had a bunch of student posters and a few discoveries, specifically by that one over there, Amanda, kind of brought me up to a point where, wow, I think I can say something a little bit new. So I slapped this together, and it's going to go all kinds of places, all right? First thing is, of course, you got to know where we're at. So this is where, like we're here, right? Now, what I'm studying generally is often down here. So just pay attention to that spot, and we'll go back. This is a long time ago. This is a long time ago. Dinosaurs had a bad day on this day. This is when you don't swim in Kansas. Trust me. Nor here. Wouldn't do it now either. And here. Anyway, okay, we're still in the Cretaceous. Most dinosaurs in Jurassic Park are, in fact, Cretaceous dinosaurs because the Cretaceous was so darn long. Now we're in the Jurassic. Safer to swim, by the way. This right here, Zion National Park, is made of that rock, and so is Roadrunner series. All right. Now we're still in Jurassic. There'll still be dinosaurs. Now we're in the Triassic. Notice that Africa is over here. South America is over here. Jurassic was rough. Whoa, I'm going the wrong way. Let's just get through all that. Back to the Devonian when the first vertebrate walked on land. The Silurian, which is, you notice that we do have water in the Silurian. And so if you drill straight down here, Silurian limestones, if you go to the west on 24, you actually see some reefs. It's not old enough. We go back to the Ordovician, and that's kind of where I'm working. And we're talking about mainly an entire region, so working with some subsurface stuff all over Ohio, Indiana, venturing as far out as Iowa, if I got my states right, and but mostly in Kentucky and Ohio and southeastern Indiana. And what the point is that when we look at the past and we look at the fossil record, we're all aware of all these reconstructions of critters. Ultimately, these reconstructions of what was living at any given time depends on the fossils that we get at any given time. Now, everybody knows that there are some fossils that are like super rare, so they're completely unrepresented, or so unrepresented that the day you find it is a lifetime find. So, for example, some little itty-bitty arthropod that they have to slice through the rock, photograph each layer, and then reconstruct like a CAT scan is something that we don't study a lot and we don't see it a lot, and it's also not preserved very often. And this is largely because they have soft parts. So right here we have a trilobite, which are common. What's hard to discuss with people is that trilobites' legs weren't really skeletonized. They weren't hard, they weren't mineralized. I mean, they still had an exoskeleton on them, but they were all organics, proteins. So when you find legs preserved, it's kind of exceptional. It's rapid burial, it's weird anoxic chemistry. And so if you find a trilobite with legs, don't show it to the professor. Basically it. The next thing is things that with multi-part skeletons. that we don't often see preserved as multi-part skeletons. The most common one at this age in the Ordovician 450 million years ago is the Echinoderms skeletons. And the Echinoderms skeletons are, why does nobody sit right here? This is like my neck's going to hurt at the end of this talk. It's like swinging back and forth to look at people. I'm gonna favor them. You know this, right? Because I'm kind of right-handed. Good Lord. So, at any rate, what we see here is a starfish on a coin known as an Edero-asteroid. Weird echinoderms from back in the day, but they're made of a bunch of little tiny plates called ossicles. If you wait more than a couple of days to bury that dead, let's say, starfish, right? The starfish will fall apart into a bazillion little tiny ossicles. Which means that if you find one of these whole, don't show it to your professor on the field trip. The next thing on the list of things in durability and increasing durability is actually a pretty common fossil. It's a snail or a clam. But if you look at snails or clams, they've obviously been recrystallized. So if you look here, these crystals are not sort of the natural lamellar or layered structure of a seashell. If you break a seashell, it breaks in layers. But these fossil snails and fossil clams are all recrystallized into this random mosaic of crystals, which means that at some point in the ground, they are disappearing and being replaced. Now, the process exactly, do they dissolve away and then get filled? That's kind of what it looks like. Or does it recrystallize in place? And I've seen evidence of that as well. So that makes these weak. If you bury them, leave them under the sediment for a while, and then rework them, you may destroy them. Right, so the process of fossilization, so I don't even count these in this talk. These two here are so uncommon that it's not worth my time to try to study them. But I do find a lot of snails, and I find a lot of places without snails, and I scratch my head and wonder, did this rock originally have snails? Does it originally record a time when there were snails? And they're just gone. The next thing up is shells made of calcite. So these are just two different crystal structures of the same chemical, calcium carbonate. All seashells are pretty much calcium carbonate. But the outside of an oyster shell is calcite and lasts forever. And the inside of an oyster shell, the nacre, is aragonite and doesn't last forever. Brachiopods, which are very common back in the day and not so common now, were all made of calcite. Now I've got to think, do I mean all? I'm going to go with all. All made with calcite. And so they are very well preserved generally, but they also show signs of wearing away, fragmenting, and disappearing over time. And then finally, I'm going back to this critter here. These ossicles fall apart, but once the ossicles, this is a brittle star arm, by the way. Confuse vertebrate paleontologists to death with that. Post that on Facebook. Is that the backbone of a frog? No, guess again. This is the arm of a brittle star, and it's made of these bunches of ossicles. Not just the central vertebral column. They're actually called vertebrae. They aren't vertebrae, but they are. And bunches of plates around it, if you've ever played with a brittle star. I accidentally pulled the arm off, okay? So, you know, I had to make a section. But at any rate, these individual plates are porous, and the pores filled with new minerals. And even though the mineralogy is kind of unstable, it rapidly recrystallizes, then it fills with, the pores fill, and these little particles last forever. So they last through burial and re-exhumation over and over and over. So the question is there some sort of bias? Again, forget those. Between this, this, and this, where if something's sitting around for a long time, will it throw off my measurements? Will it throw off my count? So I'm counting fossils like that guy in The Gods Must Be Crazy, counting elephants. 1, 2, you know, this is actually a thing that people do, right? So the issue comes down to it being more complicated than the old-fashioned concept of depositional environment. And the old-fashioned concept of, and I'm saying old-fashioned because it's current, but it is old-fashioned to me, of depositional environment is that if I find a certain kind of rock, it indicates a certain kind of environment. And if I find a different kind of rock, it indicates a different kind of environment. The simplest way to say that is I've got these rocks here that represent this super tidal above the high tide. These rocks here, which have different features in them that represent upper part of the tidal range. These rocks here that represent the lower part of the tidal range. These rocks here that are in the lagoon. And these rocks here that are off this sort of little barrier reefy thing, right? And that if I find a difference in the rock, it reflects a difference in the original environment. Like I can say, okay, so it was different. It was a different depth. It was a different water energy or something like that. So based on that, there's an old 1960s classification by a guy named Dunham of limestones that was based on energy levels. And the way he did this is he recognized, okay, there are fossils. And so these are snails, by the way. You notice the snails are on this end of the range? Well, that's going to be kind of important later. Notice that there's actually a lot of echinoderm bits over on this end. I'm kind of giving it away, right? So what's going on here is the way Dunham interpreted this is with increasing energy of the waves, you would get increasing washing of the rock. The mud would not be stable there. It would go away. It would be washed away. Like on the beach, the sand is perfectly clean, right? I mean, depending on how many people have been there. But the sand is generally clean on a beach because the waves are constantly washing it. If you go offshore, the grains get finer. And if you go further offshore, they get finer still. So the interpretation is increasing current energy as you go to the right, more fine-grained material here, and then more coarse and coarse fossil fragments here. But between the fossils, this clear area is where there was nothing. And then later, as the rock formed, it filled with crystals, right? So if I have a hole in the rock, eventually it fills with a geode. Well, this is true of just about every rock. So a pile of seashells with no mud in between them will then be filled with crystals. So lots of crystals, interpreted as high energy. Mud that's where there's so much mud that the fossils are just randomly floating in the mud is interpreted as very low energy. And when there's only mud, it's interpreted as very low energy. There's a little problem with this in that fossils grow in place. So the guy who designed this was basing it on sand, which has to be transported into a basin. Fossils can grow anywhere. You can get gigantic fossils without mud at all in a really deep ocean. It's possible, right? So right off the bat, a little problem with calling a grainstone, because it's all grains and no mud, a high energy deposit right off the bat, just because of your classification scheme, is a little iffy. Now, this goes back to the rocks I've been working on. What we tend to find in the Cincinnati region in the Ordovician is, now this is a stratigraphic diagram. How many of you are familiar with this? geologist on this side, somebody who's done archaeology. You. The rest of you are cultural anthropologists, I take it, or something else? All right. I'll just explain this really quick. So each of these is a layer, and this is a way of designating layers, and if they stick out further, they're like harder, or they're coarser grained. So if we had a conglomerate, it would be sticking way out because it's got big rocks. Sandstone a little bit less, a siltstone a little bit less, a mudstone way back here in the gray. Various symbols in here mean various things. Let's not worry so much about that. But basically, this shows layers of shells accumulation. So each of these beds is a shell accumulation. Then layers of mud with thin layers of shells. And then more layers of thick shell accumulations. And there's also a tendency for these layers to be muddy themselves, so the shells mixed with mud, supposedly low energy. And up here, these tend to be mostly shells and not so much mud. So the grainstone and the right-hand end of the classification scheme, so if we look back there, the big thick limestone deposits tend to be dominated by this kind of rock with lots of crystals, lots of open spaces. And between them, there tend to be shell beds, limestones, shell limestones, that are dominated by the mud. Now, storms were a really common feature of the region because we were lying between the equator and 20 degrees south. My how times have changed. But new model that we've kind of developed for how the deposition works is not that storms made the beds, which is kind of an old one, but that storms acted on the surface of the seafloor according to how, just randomly, right? And that accumulation changed rate. So sometimes you get a lot of mud coming in. So you may start with mud, and then you start a period of no mud coming in. You grow a community. Critters grow on the seafloor. Then a storm comes in, brings a little mud, knocks down everything, fossilizes stuff. Then another storm comes in, brings no mud, and just digs everything up. Then a storm then we recolonize that surface. Then we recolonize that surface, and we recolonize that, and so we actually get sort of a succession. As shells build up, critters grow on the shells, and the critters that grow on the shells are different from the ones who live in the mud. So we have a lot of issues when we have a long period of no deposition, where what we're fossilizing is what? Like this big, long period of mixing. So an alternative interpretation is that if we don't spend too much time accumulating, we get a lot of mud and a few shells. If we spend a little more time accumulating, we build up shell sands. So this grainy stuff is little bitty shells that have broken from previous generations. And if we spend more time, we get a bigger accumulation of fragments and still some fresher critters that have lived there. And then things just keep winnowing and building and winnowing and building until we have a really clean accumulation of shells. And then eventually it just sort of goes nuts. And what this shows is the accumulation of diagenetic products, which is things that form in place because the chemistry is just sitting there. And so over time, has anybody heard of manganese nodules? Manganese nodules on the seafloor. The seafloor is very stable in that there's not a lot of sedimentation. And the seawater contains chemistry. That chemistry deposits in place of mud. In other words, the mud does not dilute the chemical actions. Right? If we have rapid deposition, the chemicals don't build, you know, you lose them. You don't have them concentrated. They're still there. You still have manganese in the sediments, but you don't have a chunk of manganese that big around that you can pull up and use as an ore. So slow deposition, in this case, generally leads to the accumulation of phosphate. And I already talked ad infinitum about phosphate, and I'm tired of it. But it's important for the entire story. Well, okay, we'll talk a little bit about phosphate. So here's what you get. We get these little tiny snails accumulated in a bed where you can't find any grown-up snails. And the reason you find these little tiny snails is that this is a product of seafloor diagenesis, where you build this material that's almost indestructible. But it only occupies tiny, tiny, tiny spaces. And so you get this really weird picture of the seafloor with tiny snails. Now, by the way, tiny snails are everywhere. It's just nobody notices them because they're big snails to look at. But when you destroy all the big snails and all you notice is the tiny snails, you think, gee, that's weird. But does it reflect the environment or does it reflect time of accumulation? Tested that. So this is Amanda's little study. This is like 3 posters in. There are 3 student posters in this talk. Amanda got under the microscope and, like elephants, started counting those little dots. Right there. Those things. 1, 2, 3. Well, this was an estimate. This was our first pass. The counting is actually more interesting, but I didn't have time. And preliminary results were, this is a chi-squared kind of diagram, and dark red is like nutty, out of line with what you'd expect for random, way high. Pink is really pretty high, and light pink is high, and lighter pink is pretty high, right? It just gets higher and higher as you go up to reds. This is like not random. This whole diagram is not random, and I'm not very good at statistics, so I'm still working on this. This whole diagram is not random to the 0.000000 something confidence interval. There's like a lot of zeros there. So I'm not p-hacking. But here's the interesting relationship. We get very little of these diagenetics when we are looking at muddy rocks. And then we get a sudden jump into where the most crystalline rocks, the grainstones, are also the higher above expected from random of all the rocks, right? So this fits the prediction, or this fits the hypothesis that instead of directly reflecting depositional environment, these things reflect time because, again, diagenetic products take time. Chemistry takes time. Everybody knows this. They're failing, right? Who's in chemistry? Poor kid. These are all failing, all of them. It takes time. This is why you've got to do grainstone to do chemistry. All right. So an alternative interpretation is that we're increasing depositional rate to the left instead of increasing wave or current energy to the right. And that's a paper. So because, everybody's used this class of, what I hate about science sometimes is it becomes dully descriptive. You go, okay, that's a Dunham grainstone, that's a packstone. We got 3 packstones here, and then we got another grainstone, and nobody thinks about it. They do that description and they're gone. So it's high energy, man. All right, so just a bit of evidence of time beyond the phosphate. Paul, one of our students who came back after a long career as a lawyer and wanted to do something fun, I gave him this project, and that was, check this out. That's black. Anybody been to the beach and seen black shells? Right? Go to the beach and see black shells, there's a half of a good chance that that beach was replenished by dredging. And that what the black shells are generally is Pleistocene in age or older. Here we have a single bed that we collected the mud right above this bed plus the bed itself. So we take the bed, scoop it up, and there's mud above it. And in the mud, there are hundreds and hundreds of shells. And on the bed, we have light shells, medium shells, and dark shells, just like on that beach in Jacksonville, or wherever you go to find shells on a beach where they've done some beach nourishment, you will find these black shells. And it may be more than that. I don't study that very well because I go to other places I'm not supposed to go and still find black shells under bridges and things. So just to emphasize this, light shells, dark shells. Now look at this pattern. Notice that these are more abraded, that the surfaces are crisper here, right? Just as in the modern, the black shells appear to be, to have been subjected to abrasion. That is, they appear to be older. They appear to have been subjected to abrasion. So we find in one bed, black and non-black shells. Now, just to get an explanation of this, I sliced a bunch of shells, light shells here on the top, dark shells on the bottom, and it's really hard to see. But you notice there's this dispersed black material in here. All right, we'll look at it closer. So in a light shell up on the top, if we do element mapping, iron and sulfur are just quoted yellow. That stuff's black when I look at the light photograph of it. That's called pyrite. Now, pyrite forms in the muck when there's low oxygen underneath. So if you turn over a rock in the pond and it's black and it smells bad, there be making pyrite, right? Iron sulfide. The sulfides are what gives it the bad smell. That as we go down, we'll just skip to the bottom, the pyrite gets more extensive, and this pyrite is in a natural pore system. So these are natural pores that are already in what I'm saying natural, it's all natural. Biological, well, could be bacterial. Give me a minute. The brachiopod made those pores. The seashell itself had those pores the day that the animal died. And so those pores are filled with pyrite. But in the one that's the blackest, the pyrite is scattered throughout the shell. The shell is falling apart. On the inside, it's delaminating like an old bone sitting out on the desert floor. Right? So we show evidence directly that even though there's pyrite everywhere, that the pyrite permeates the shell because the structure of the shell weakens over time. And that's what causes the blackness in these shells. I have a whole collection from Jacksonville that anybody want a project? All right. So that's kind of just a few lines of evidence that there's something going on with deep time. Now, this is a study that I did with Rebecca Freeman who's at University of Kentucky. And what happened is this old man here, who's an amateur fossil collector in Cincinnati, had found these shells. And I'll just go back to that. He'd found these shells that had these little, they're all brachiopods. So one big brachiopod, and he thought that these little brachiopods were like embedded in the shell of the big brachiopod. And I'm like, no, that's not possible. But I gave it the doubt that they could have been pearlized in there and then got up in between the mantle and gotten trapped. But the story was actually more interesting. The reason he thought they bored into it. They'd actually drilled holes like a shipworm into the seashell. And sometimes when you deal with amateur collectors, you have to deal with theories. Although the guy at the National Museum who had them in his collection also thought he might be right, I was, no way. There's no way. So I looked at them, but the reason is these things generally in the modern live in the mud. They live in very harsh environments, possibly because it's too harsh for them to compete nowadays in non-harsh environments. But they're edible from here down in the Philippines. And the top I wouldn't eat. I just advise against it. But they live in the mud, they live in burrows, and they stick their little feeding apparatus out the top of the burrow. When we did sectioning, what we found was that the reason he could see them, and here's one here, here's one here, and here's one here, and here's one here. The reason he could see them at the top of the shell was because the crystals that had formed just below the surface of the shell had molded the inside of the shell. And when the shell itself kind of spalled off, flaked off the top, it looked like you still had a shell. It looked like they were embedded in the shell, but really they were trapped under the shell. So this was interesting. They were trapped under the shell because of their escape response. And these things were alive. The shells, the big shells, were dead. But what had happened is a storm had come through, reworked everything, and then the big trash can lid shells fell on everything, concave down, and there's only really one escape response if you get buried. And what is that if you have a simple to no brain at all? Go up. And if you hit a dome going up, you try to keep going up, and you're going to get trapped right in the middle if you don't have much of a brain. Hell, if I got buried, I'd get trapped under a dome, right? There's no way I would go back down and try to get back up. I would die. So I'm not gonna insult these guys that bad. It was a bad day. Give them a break. So what's interesting is we look on the surface, you have to ask yourself, okay, these big trash can lid shells are called Raffinaskina. I study Raffinaskina because I can always guarantee to find it. Right? That's why I don't do dinosaurs. It's just a pain. But that's the reason I got called in on this. Look at this Raffinaskina thing. Well, okay. The question is, was this a community of Raffinaskina? Well, the problem is there wasn't a single articulated set of valves of Raffinaskina in the entire. We sliced and we sliced and we sliced because you couldn't get them out of the rock. You have to slice through them. We did not find one, not one Raffinaskina that had been buried alive. Yet, these little critters here, each one of them has both valves, crystals in between, like they clamp shut, filled with nothing, crystals filled in later. They were buried alive. So they were alive, trying to escape, accumulated in massive numbers under the shells, but the other species didn't exist anymore in the environment. It was only its ghosts. It left a curse on its death. And the paper was called The Curse of Raffinaskina. All right, so this is an example of ecosystem engineering. It also illustrates my main point here, is that when we look at the rocks and we count fossils, what are we counting? Because to this point, the only thing we could definitely say was alive in the whole set of beds was those little things trying to escape, that we can definitely say was alive. There's a lot of things that are fragmented. So ecosystem engineering is when the presence of one critter modifies the environment for or against another critter. And in the fossil record, there'd been all kinds of documentation of positive ecosystem engineering with this very species of trash can lid shells. These shells are almost always covered with something else, and without those shells on the muddy surface, these something else's, this little spidery growth right here, a bryozoan, could not have lived. These Edrioasteroids, starfish on a coin, could not have survived without something to attach to. These other brachiopods and these bryozoans that grow into branched colonies could not have survived without the shells to attach to. Dead or alive, some debates in some cases, but dead is plenty good for most of these things. This was the only case of negative ecosystem engineering that had been documented that we know of. Like, it was really bad for the little lingulid brachiopods that these big shells existed. It made their burrowing life hell. And so we also see, if we study this further, that this very bed contains a record of succession. And I'm not going to go too much, but basically what we see as fossils doesn't necessarily represent the living community. It's a mixture of living communities and dead communities. Again, evidence of time. We did point count this, and by we I meant she. Rebecca point counted this and tried to quantify, and I think I forgot to put anything down. So this is a slice through that very bed, and you see a very few of these very large shells here. You see a dead trilobite here. You see all kinds of little fragments here. Most of the bed is fragments of past lives. So if you imagine the seafloor with shellbed sand everywhere and a few things alive, everything else is dead. So this gives us the concept again that there's a certain succession in the Ordovician, and that as we preserve that bed, we are preserving the last and then the next, but maybe not the first few sears, levels of that succession. So if I were to count these fossils, the ecology that I come up with may be crap if I'm not aware of the taphonomy. So it appears to be, from our studies, that we start with mollusks dominated. So here's a complication. Mollusks like to burrow around, they like to dig. Clams like to live semi-infaunally. Snails like to crawl on mud as well as shells in some cases, depending on the snail. Snails are like, do anything you want, except fly, unless they're birds, and feet do it. Anyway, snails will do anything. But there's a double whammy on snails. Did the snails exist initially because they're the first level of colonization and then are replaced? Or do the snails not show up so well in more aged bed accumulations because taphonomy takes them out, as I discussed earlier? Oh, so much to do. There are all kinds of projects. So first mollusks dominated, then Raphinaskina dominated, then more diverse, and then dead. Morbid sense of humor. All right, so one of these beds has really complex histories, and I like written, that's 2 papers out of 1 bed, which the oil people laugh at me with. All right, so the next one is same brachiopod, Raphinaskina. The problem of snails is a real painful issue because you've got a confusion as to whether you had the snails in the first place and they were lost, or whether the snails don't exist anymore because of ecology, right? So there's ecological changes because of the bed, because of ecosystem engineering. And then there's also taphonomic changes. And but I figured out something, right? So a long time ago when I was doing my dissertation, I measured the sizes of Raffinaskina on everything and never included it in my dissertation. I didn't know what to do with it until last semester when thinking about Amanda's project. All right? I didn't know what to do with it. But here we show giant 1 millimeter here. So here's like a 0.5 millimeter newly hatched shell growth line. And then there's another growth line about here that might be meaningful, right? And here's an interesting observation. So using data from my, who cares? Anyway, so I went through a bunch of rocks and I looked at Raffinaskina sizes specifically to try to find babies. So here's a really tiny, that's 0, 1, 2, 3, 4, 5, 6 log scale. So 2 to the first, 2 to the second, 2 to the third millimeters of things that I was able to measure on the surface of the bed. Hinge size, or half the hinge, because they were all broken, so I could find more half hinges than whole hinges. So measuring from here to here, this is what I'm looking at, and what you notice is there are almost no frickin' babies. Very few babies, and you don't expect this with living things because living things tend to die more often as babies. And even if they don't die more often as babies, they at least die some as babies, right? I mean, we could get more specific, right? This seems to be that I expected something. And this is an observation that was made generally, has been made. Where are the Raffinaskina babies? So, first hypothesis is that they grow really fast. So, let's look at growth lines. Let's assume that the growth lines are more or less regular. Let's also not do this alone at night, but give it to a student next time. So I drew some growth lines on these shells to just try to get a little bit of a handle on it. Measured the distances of each increment, so growth line number here, and then how much did it grow at any one point. And on that one, I got some idea that it grows slow at first, fast, then slow. So this doesn't really fit the concept of so rapid a growth that you don't actually have a baby phase to deal with. Here's another way of accumulating the data. Just accumulate total length by adding all the growth lines together. And you get a fairly standard growth curve, right? You start out a little bit slow, grow fast, and then level off. No evidence there that they grow really fast. Hypothesis 2. It might have been so slow growing and long-lived, it had solid type 1 survivorship like human beings. I mean, again, except even human beings die when they're babies. So you get some kind of bump. And so it still doesn't help. Okay, well, I'll give them type 1 survivorship for, conservative purposes. I'm not going to say that they were, like frogs and just die. But the hypothesis 3, this is back to Rebecca's study on that previous bed, where she colored everything. Check out all these little teeny, itsy-bitsy, thin fragments. I have no idea because the microscope study is so difficult. Okay, I have a little bit of an idea. A lot of these are probably baby Raffinaskina. And so they disappear from our sight because when they become fragments, they're no longer fossils. And this is a matter of how people do science. When do you call it not a fossil anymore? Well, it's when you can't recognize it anymore. So, to test this, remember we had that classification of limestone. So here's the distribution of the different kinds of limestones: grainstones with a lot of crystals, whack-pack and mud silt with very few fossils and a lot of mud. You notice that just the percentage of mud, which is this dark green, goes pretty well with the overall composition of the limestones. So if we take just the mud percentage curve and plot it against the sizes of these shells where you find them, there does seem to be a pattern where you get the big black areas where there's mud, that these things go way down, right? And so the hypothesis would be that the overall size isn't changing, which is a complication because they could be smaller in different environments, right? But if there are more babies and you still have the similar maximum sizes, then you might be onto something. And by you, I mean me. So we organize it by shale percentage, and lo and behold, maximum size appears to stay similar. Minimum size goes down as we get more and more mud in the system. More and more mud means more rapid burial, less time sitting around to break. Tried various ways of seeing this, and this is where I could use some help if anybody's really good at statistics. You know, I'm seeing this side growing as you go from red, which is no mud, to blue, which is some mud, to green, which is a lot of mud. And should I quit yet? Oh God, yeah, okay. And again, this is where we normalize that whole thing, and there seems to be an entire shift. And so the more mud, the smaller, and there's a different skew. And if we break it right there, it looks really impressive. Right? So if we break right there at 45%, then we get this impressive difference between the red, virtually no mud, and the green, a lot of mud, where you see a lot of babies preserved. So this seems to support it. We could also do limestone maturity. And, well, again, the red one is way off to the right. This is the most mature limestones. And what do I mean by mature? Lots of crystals, no mud. And these are the muddy limestones right here. Now, again, my statistics isn't great. This is like off the cuff. But, and there's this one. So, I think that's it. There's these conclusions are from different presentations, but basically, I think we have a lot of lines of evidence that, you know, when you take one species, you kind of eliminate ecological factors from picking and choosing. When you say the babies are delicate, right? The whole thing is there are certain things that are delicate and they don't last through the process, and there are other things that are robust. And if you can get one species, you can kind of tease that out from ecologies, you know, where the delicacy is somehow correlated with their ecology, and they're at an earlier time or don't occur in certain environments. And that's about it. Thank you.
So you're talking about the succession that you're seeing in these forest communities. How much of that is based on what is known about current day ocean communities? And do they ever cite the original studies on forest succession that were done here in the great state of Indiana?
All right, number one, I don't know. So the successional stuff was done in the 1960s. So the two successional diagrams that I showed were in the 1960s, and very rapidly thereafter, somebody poo-pooed it and said taphonomy wipes it out. And that basically what had happened then is the person had stated, I can see at the bottom of the bed is one seer, one level of succession. The next level I see over top of that, and the next level I see over top of that, and the next level I see over top of that. And people rapidly pointed out over the next 10 years, this is how rapid things go in geology, that the whole bed is mixed. And you can't see that, right? And of course, anytime somebody says can't, I'm like, oh, dear me. So what happened when we studied the one problem that the guy had pointed out about lingula inside of Raffinaskina was that we started looking at the thin sections, and I said, like all the fragments are mollusks. Like the fragments are dominated by mollusks. The Raffinaskina are all dead, and there's very few things that look like they were alive at the time that this thing occurred, right? Now, there's been a body of work that has run kind of isolated from modern biology, and this is a big problem in paleo and in biology, both ways. They don't cite each other. Which is like when we get down to writing the paper, we generally try to dig into everything. So I'm aware of modern studies in ecosystem engineering, because the minute we post this stuff on the intertubes, we had a bunch of people like citing it and asking us to present at like dredging conferences, right? This kind of thing, because this is relevant to dredging. If throwing shells on top of the seafloor is going to trap the current community, that's an issue. So that was forced upon us. We were forced to kind of recognize it. We haven't really published the second paper, though, on the whole structure of the bed. We keep getting bogged down in stupid administrative things, like closing departments and things. So we'll do that, though. Yes?
Maybe this isn't a geology question, but those little creatures that are in the sand, you know, you talked about how if you were in the sand, you would dig for the top, and those little creatures, how do they know what direction? I mean, how do creatures in sand know?
Not an anatomist.
Okay.
I'm almost certain that everything has something like statoblasts or some kind of rock in the ear, you know, something that rattles around in their body and tells them which way is down. But I can't go past that on lingulids. But I could ask my co-author. She's actually the lingulid expert. There's probably a study. Yes?
What was the main, time period for finding all of these fossils?
So I spent most of my time thinking about 450 million years ago. Talk about living in the past. 450 million years, and the name of it is the Ordovician. And we usually, as geologists, go by the name because the numbers get confusing. So this is the Ordovician. Larry.
Since limestone is so essential to purifying water and everything, is your real message that we have these tiny mollusks from the past to thank for bourbon?
Yes. And actually, yeah, some of the rocks I study are right next to the one that has low rye. What is that one? Maker's Mark, yeah. You know your bourbon. Like that's the break when we're tired of field work and we're about to die of heat. I don't know that it helps to taste bourbon while you're doing that, but they have water too.
Are there any species where the baby problem isn't as much of an issue? Like, are babies easier to find?
Yes, and to check out the difference. Oh, come on. Slow, slow. There you go. Look at that. These things are ribbed. But you got things that are plenty smaller than the biggest ones there. And if you look really close, you can actually pick up really tiny ones pretty easily. And the reason is they're corrugated. So since they're corrugated, they're much stronger. Most modern studies of taphonomy have noted a serious difference between babies and adults.
Thanks for being here for our last talk.
Thank you.